two particles, separated by the entire width of the observable universe. One of them is measured, and in that single instant, before any signal, before any light, before any force in physics could possibly travel that distance, the other one already knows. Not guesses, not approximates. Knows, with absolute certainty, with the kind of precision that would make every law of classical physics quietly fold itself in half and disappear under the table. This is not a metaphor. This is not poetic license. This is what actually happens in laboratories on this planet, confirmed thousands of times over decades with instruments so sensitive they can detect the spin of a single electron. And the fact that it happens should terrify you, because what it means about the nature of reality is something most physicists still cannot fully accept. We were told from the very beginning of our education that the universe has rules, that information cannot travel faster than light, that two objects separated in space are by definition separate, that what happens to one cannot instantaneously affect the other. These rules were not casual suggestions. They were the foundation of everything. Einstein built his entire theory of special relativity on them. Causality, the chain of cause and effect that prevents grandmothers from being unborn before they have children, depends on them. The entire logical architecture of physics, the very idea that space and time mean something, rests on the assumption that locality is real, that things exist in places, that distance matters. Quantum entanglement says, no, distance does not matter. Locality is an illusion. And two things that were once connected remain connected in some deep and inexplicable way no matter how far apart they travel. Measure one, and you instantly know the other. Change one, and the other responds. Not eventually, not after some delay. Instantly. Einstein hated this. He called it spooky action at a distance, and he did not mean it as a compliment. He meant it as an insult, as a way of saying, this is clearly absurd, this is clearly wrong, we must be missing something. He spent the last decades of his life trying to prove that quantum mechanics was incomplete, that behind the apparent randomness and the apparent non-locality there were hidden variables, real definite properties that particles always had, and that our equations were just too crude to see them. He was certain the universe was not this strange. He was wrong. But here is where it gets more complicated than a simple story of Einstein being wrong, because his instinct was not irrational. His demand that reality makes sense, that particles have definite properties before we measure them, that no influence can travel faster than light, these are demands that any reasonable person would make. And for a long time there was no way to test whether he was right or wrong. The debate between quantum mechanics and hidden variable theories was philosophical, not experimental. That changed in 1964, when a physicist named John Bell sat down and did something remarkable. Bell proved mathematically that if hidden variables existed, if particles truly had preset definite values before measurement, then the statistical correlations between measurements of entangled particles would have to stay below a certain limit. He expressed this as an inequality, a mathematical bound. If experiments violated this inequality, if the correlations between entangled particles were stronger than any hidden variable theory could possibly explain, then local realism, the idea that particles have definite local properties, was dead. Bell essentially created a test, a real physical experimental test, and then physicists ran it. The results came in decades of experiments, growing more refined and more airtight with each iteration. The entangled particles violated Bell's inequality. Not slightly, not ambiguously. They violated it decisively, consistently, in ways that left no room for hidden variables, no room for pre-existing properties, no room for the universe to have secretly prearranged the outcomes before anyone looked. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger specifically for their experimental work on entanglement and Bell inequalities. The Nobel Committee did not mince words. Their work proved that nature is fundamentally non-local. The universe, at its deepest level, does not respect the boundaries of space. Let that sink in for a moment, because it is not a small thing. It is not a quirk of exotic particles that never appears in the real world. It is a fundamental feature of how reality works. And it does not just challenge our intuitions, it challenges the entire conceptual framework we use to understand what exists. To understand why entanglement is so shocking, you first need to understand what a particle actually is, according to quantum mechanics, which is itself a deeply uncomfortable story. A particle, before it is measured, does not have definite properties. It does not have a definite spin, a definite position, a definite momentum. It exists in what physicists call a superposition, a simultaneous combination of all possible states weighted by probabilities. The electron is not spinning up or spinning down. It is spinning both up and down in a precise mathematical combination until the moment you look at it. The moment you measure it, the superposition collapses into a single definite outcome. The electron picks a value. This is already deeply strange. But entanglement takes it further. When two particles become entangled, which can happen through direct interaction, through creation from a common source, through a variety of processes, their superpositions become linked. The combined quantum state of the two particles cannot be written as two separate states. It is one single state, a superposition of two particles together, regardless of how far apart they travel. When you measure one particle and it collapses into a definite value, the other particle instantaneously collapses too into a correlated value. Not because a signal was sent, not because they communicated, but because they were, in some sense that defies ordinary spatial intuition, still one thing. Here is the experiment that made this real, the one that started everything, the one that has haunted physics ever since. Imagine you create two photons in a special process called spontaneous parametric down conversion, where one photon passes through a certain crystal and splits into two photons whose polarizations are entangled. You send these two photons in opposite directions. You let them travel until they are separated by a large distance. In some versions of this experiment, the distance is measured in kilometers. Then you measure the polarization of each photon. You do this not once, not 100 times, but millions of times, in every possible combination of measurement angles. What you find is that the results are correlated in a way that cannot be explained by any pre-existing agreement between the photons. If the photons had been carrying hidden instructions from the moment they were created, if they had secretly agreed in advance what results to give for each possible measurement, the correlations would be limited by Bell's inequality. But the correlations are not limited. They are stronger. They are exactly as strong as quantum mechanics predicts, which is stronger than any local hidden variable theory allows. The photons are not carrying secret instructions. They are genuinely undecided until the moment of measurement. And when one decides, the other decides too, instantaneously, regardless of distance. Now, here is the question that every physicist, every philosopher, every person who hears this story eventually asks. Does this mean information is being transmitted faster than light? Is entanglement a way to send signals, to communicate instantaneously across any distance? And the answer, frustratingly, fascinatingly, is no. You cannot use entanglement to send information. When you measure your particle, you get a random result. You cannot control what that result will be. Your colleague on the other side of the universe also gets a random result. The fact that your results will turn out to be correlated is only visible when you later compare notes through an ordinary, light-speed limited channel. You cannot use the correlation itself to send a message, because you have no control over which random outcome occurs at your end. This is called the no communication theorem, and it is what saves the universe from paradox. If you could use entanglement to send signals faster than light, you could also, according to special relativity, send information backward in time. You could create causal loops. You could know the results of things before they happened. The no communication theorem prevents this. But notice what it does not prevent. It does not prevent the non-local influence from existing. The correlation still happens instantaneously. The connection is still real. We just cannot exploit it to send a message. Nature seems to have drawn a very specific, very deliberate line. You can have non-local correlations, but not non-local control. Why? No one knows. This is one of the deepest open questions in physics. It feels almost like a rule that was designed, like someone built the universe so that it would be deeply non-local at its foundations, but would still appear local to anyone trying to use it. Some physicists find this suspicious. Some find it elegant. Everyone finds it strange. But let us now follow the strangeness deeper, because we have only been at the surface. The experiments we described involve particles being measured simultaneously, or nearly so. What happens when you introduce a time delay? What if you could choose whether to entangle particles after they were already created, or even after one of them had already been measured? This sounds impossible. It sounds like asking what color you want to paint a house that was demolished last year. But quantum mechanics says this is not impossible. And the experiment that proved it is one of the most mind-bending things humans have ever done. It is called the delayed choice quantum eraser experiment, and it was first performed by Yoon Ho Kim and colleagues in 1999. The setup is an extension of the double-slit experiment combined with entanglement. Here is the basic idea. You fire photons one at a time at a double slit, and under normal conditions, each photon goes through both slits simultaneously. It is in a superposition, and the photons collectively build up an interference pattern on a detector screen. a pattern of alternating bright and dark bands that is the signature of wave-like behavior. The pattern exists because the photon takes both paths and interferes with itself. Now you add entanglement. Each photon that goes through the slits produces an entangled partner photon. This partner photon can be measured in a way that either reveals which slit the original photon went through or erases that information, making it impossible to know. If the partner photon reveals the witch path information, the original photon behaves as if it went through only one slit and the interference pattern disappears. If the partner photon's witch path information is erased, the interference pattern returns. This alone is remarkable, but not entirely shocking. It is a version of the observer effect, the idea that measuring one part of a quantum system affects the whole. The delay choice part is where it becomes truly disturbing. In Kim's experiment, the partner photon arrives at its detector after the original photon has already hit the screen. The decision about whether to reveal or erase the witch path information is made after the original photon has already landed. And yet the original photon's behavior, whether it shows an interference pattern or not, corresponds to what happens to its partner photon in the future. The present outcome appears to be determined by a future choice. Read that again. The photon that has already landed on the screen somehow knew at the time it was travelling what was going to happen to its partner in the future. If the partner's witch path information was going to be preserved, the original photon behaved like a particle. If that information was going to be erased, the original photon behaved like a wave. The photon acted in the present based on what would happen in the future. Time, for a moment, appears to run backward. Physicists will immediately object, and correctly, that this does not actually allow for backward causation in any usable sense. You cannot send a message to the past. The correlations between the two sets of results only become visible when you compare the data afterward, through ordinary time-forward channels. The no communication theorem holds. But the fact that the correlations exist, the fact that the photon's behavior at the screen is statistically linked to what happens to its partner later, is real. It is in the data. It happened. Whatever story we tell about it, it happened. And this brings us to the interpretations. Because quantum mechanics, unlike any other branch of physics, does not come with an agreed-upon story about what it means. The equations work. Everyone agrees on the equations. But no one agrees on what the equations are describing. And entanglement, more than any other phenomenon, is where the interpretations diverge most dramatically. The oldest interpretation is the Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, formulated in the 1920s. Copenhagen says that quantum mechanics is simply a tool for predicting measurement outcomes. Asking what is really happening between measurements is a meaningless question. The wave function is not a description of physical reality. It is a catalogue of probabilities. When you measure a particle, the wave function collapses, and you get a result. Do not ask where the collapse happens, or what causes it, or what was there before. The theory works. That is enough. For decades, Copenhagen dominated. It was practical. It allowed physicists to get on with their calculations without getting lost in philosophy. But it always left a bad taste. It felt like a deliberate avoidance of the question. Bohr's famous quote, "If you are not shocked by quantum mechanics, you haven't understood it," was not just a clever saying. It was an acknowledgement that something profound was being swept under the rug. The most radical alternative to Copenhagen was proposed in 1957 by Hugh Everett III, a young graduate student at Princeton. Everett's idea was simple and devastating. What if the wave function never collapses? What if, instead of one outcome being chosen and the others disappearing, all outcomes happen simultaneously, each in a different branch of reality? When you measure an electron and find it spinning up, you split into a version of yourself who measured up and a version of yourself who measured down. Both equally real, both equally certain, they found the only result: the universe branches. In this interpretation, known as the many worlds interpretation, entanglement looks different. When two particles are entangled and one is measured, the result is not that one outcome is chosen and the particles influence each other. The result is that reality branches into separate versions, one for each possible outcome, and in each branch the particles have correlated values because the branching happens to both particles simultaneously. There is no spooky action at a distance because nothing is being sent anywhere. The correlations exist within each branch because the branches themselves are defined by the joint quantum state of both particles together. Many worlds has attracted serious attention from serious physicists, including Stephen Hawking, who found it mathematically appealing. It solves certain problems in quantum cosmology that Copenhagen struggles with. It is also, from a certain angle, the least radical option. It takes the equations of quantum mechanics literally, without adding anything like a collapse mechanism, and accepts whatever they imply. But what they imply is an uncountable infinity of parallel universes, all equally real, containing every possible version of every event that has ever happened or could happen. Some people find this too high a price to pay for conceptual tidiness. Others find it liberating. Then there is the de Broglie-Bohm interpretation, also called pilot wave theory, which takes a completely different approach. In pilot wave theory, particles are real physical objects with definite positions at all times, just as Einstein hoped. But they are guided by a real physical wave, the pilot wave, which evolves according to the Schrödinger equation. The apparent randomness of quantum mechanics comes from our ignorance of the exact initial positions of the particles, not from any fundamental indeterminacy. In this picture, hidden variables exist, they just happen to be non-local. The pilot wave extends through all of space, and when one entangled particle is measured, the pilot wave adjusts globally and instantaneously, changing the guidance of the distant particle immediately. Locality is sacrificed to save determinism. Pilot wave theory makes the same predictions as standard quantum mechanics. You cannot distinguish between them experimentally with current technology, but it tells a completely different story about what is happening. In pilot wave theory, entanglement is not spooky at all. It is simply the fact that the pilot wave is inherently non-local, connecting particles across space through a single extended field. The price is that you have to accept non-locality explicitly, built into the foundations of your theory rather than being surprised by it in experiments. There is also the relational interpretation due to Carlo Rovelli, which says that quantum states are not absolute but relative, that every quantum property is defined only with respect to a specific observer or system. Entanglement, in this view, is about the consistency of correlations between different observers' perspectives. There is no single objective quantum state of the universe. There are only perspectives, and the correlations between them are what quantum mechanics describes. This sounds very abstract, and it is, but it is also rigorous, and some philosophers of physics find it the most intellectually honest option. And finally, there is the transactional interpretation proposed by John Cramer in 1986, which is perhaps the most poetic and unsettling of all. In the transactional interpretation, quantum events happen through a kind of negotiation between the future and the past. When a particle is emitted, it sends a wave forward in time, an offer wave. When a detector absorbs it, it sends a wave backward in time, a confirmation wave. The actual transaction happens where the two waves meet, spanning the gap between emission and absorption. Time, in this picture, is not a one-way street at the quantum level. Quantum events reach backward and forward in time to negotiate their own occurrence. The transactional interpretation naturally explains entanglement. The correlation between two entangled particles is established through a four-dimensional handshake, with waves travelling both forward and backward in time between the two measurement events. It sounds insane. It also, when you do the math, gives exactly the right answers. No one is sure whether to take it seriously as a description of reality, or to treat it as a mathematical trick that happens to work. What all these interpretations have in common is that they are trying to answer the same terrifying question. What kind of universe is this? What does it mean that two things can be separated by billions of light years and still be connected in a way that defies locality? What does it mean that a particle has no definite properties until it is measured? What does it mean that the present can be statistically influenced by the future, or that reality might branch infinitely with every quantum event? The honest answer is that we do not know, not the way we do not know who built Stonehenge or what happened before the Big Bang. Those are gaps in our information, and we might fill them someday. This is more fundamental than that. This is a gap in our ability to even conceptualize what is happening. Our brains evolved to navigate a world of medium-sized objects moving at low speeds, a world where locality is always valid and objects always have definite properties. Quantum mechanics is not a failure of our theories. It is a failure of our intuitions. The universe does not care about our intuitions. But let us stop with the interpretations for a moment and talk about something more concrete, because entanglement is not just philosophical. It is also rapidly becoming technological. And what humans are now beginning to do with entanglement is, in its own way, as shocking as the physics itself. Quantum cryptography is the most mature of the quantum technologies, and it uses entanglement to achieve something that was previously mathematically impossible. Provably secure communication. The basic idea is elegant. If you and a partner each receive one particle of an entangled pair, and you both measure your particles to generate a random key, any eavesdropper who intercepts the particles will necessarily disturb the entanglement, because measuring a quantum system disturbs it. This disturbance is detectable. Any attempt to intercept the key leaves fingerprints that cannot be hidden. The security of quantum cryptography is not based on computational difficulty like current encryption schemes. It is based on the laws of physics. Quantum cryptography cannot be broken by a better computer, a smarter algorithm, or more computing power. It can only be broken by violating quantum mechanics, which is to say, it cannot be broken. China launched a quantum communication satellite called Meteus in 2016. In 2022, Chinese researchers used it to establish entanglement-based quantum key distribution between ground stations separated by more than 4,600 kilometers. This is not science fiction. This is an operational quantum communication network, currently in early stages, using entangled photons bounced off a satellite to exchange cryptographic keys that are, in principle, perfectly secure. The quantum internet is not a distant dream. It is something that exists right now in a primitive but real form. Quantum computing is further from practical deployment, but potentially more transformative. A quantum computer uses qubits, quantum bits, that can be in superpositions of 0 and 1 simultaneously, and leverages entanglement to perform certain kinds of calculations exponentially faster than any classical computer. The key word is certain. Quantum computers are not universally faster than classical computers. They are dramatically faster for specific problems, factoring large numbers, simulating quantum systems, searching unsorted databases, optimizing complex systems. For other problems, they offer no advantage. But the problems they are fast at include breaking most of the public key cryptography currently used to protect Internet traffic, financial transactions, state secrets, medical records. When quantum computers become powerful enough, and the estimates range from 10 to 30 years, which is a wide range but not infinitely far, they will be able to break essentially all current encryption in seconds. This is sometimes called Q-Day, the day a quantum computer capable of breaking RSA encryption becomes operational. Governments around the world are already preparing. The National Institute of Standards and Technology in the United States finalized new quantum-resistant cryptographic standards in 2024. The race between quantum computers and quantum-resistant encryption is already underway. But even more fascinating and more speculative is what quantum entanglement might tell us about the structure of space-time itself. In recent years, a remarkable convergence has occurred between quantum information theory and theoretical physics. The key concept is something called entanglement entropy, a measure of how much entanglement exists between different parts of a quantum system. And what physicists discovered is that entanglement entropy appears to be directly related to the geometry of spacetime. The specific conjecture is called ER equals EPR. ER refers to the Einstein-Rosen bridge, the technical name for a wormhole, a hypothetical tunnel connecting two distant points in spacetime. EPR refers to the Einstein-Podolsky-Rosen paper of 1935, the first rigorous formulation of what we now call quantum entanglement. The conjecture, first proposed by Juan Maldacena and Leonard Susskind in 2013, is that these two things are secretly the same thing, An entangled pair of particles is, in some deep sense, connected by a microscopic wormhole. This is not yet proven. It is a conjecture based on calculations in a specific mathematical context called anti-de Sitter space, which may or may not describe the actual universe. But it is taken seriously by serious physicists, and here is why. It would explain a lot. It would explain why entanglement creates correlations that seem to transcend space. If the particles are connected by a wormhole, the connection is not travelling through space. It is going around space, through the wormhole itself. It would also connect the two great unsolved problems of theoretical physics, the unification of quantum mechanics and general relativity, suggesting that the fabric of space-time itself is built out of quantum entanglement. The idea is sometimes expressed as space-time is woven from entanglement. Remove the entanglement and space-time breaks apart. The geometry of the universe, the very texture of space and time, is not a backdrop against which quantum events happen. It is a consequence of how quantum systems are entangled with each other. Space is not a container. Space is an emergent property of quantum information. If this is right, and it might not be, but if it is, then asking what quantum entanglement really is the same as asking what space is. The non-locality of entanglement is not strange because it violates the rules of space. It is strange because it reveals that space, as we experience it, is a derived emergent concept. Underneath space, underneath locality, there is a deeper level of reality where things are connected in ways that do not require distance, because distance itself is a feature of the surface, not the foundation. Think about that for a moment. We experience the world as a place where things are here or there, close or far. Distance feels fundamental. The fact that you cannot reach out and touch someone on the other side of the planet feels like a basic fact about reality. But if space-time is woven from entanglement, then that sense of distance is not fundamental at all. It is an approximation that holds in the everyday world, but breaks down at the quantum level. Two particles that are entangled are not far apart at a deeper level of reality. They are the same thing, expressed in different places of the emergent space-time we inhabit. This is not mysticism. This is not New Age philosophy dressed up in physics language. This is the direction that rigorous theoretical physics is actually moving. The people working on this, Maldacena, Susskind, Mark van Ramsdonk, Sean Carroll, many others, are among the most technically sophisticated physicists alive. They are not making vague analogies. They are doing mathematics. And the mathematics keeps pointing toward the same conclusion. The deep structure of reality is quantum information, and space-time is what that information looks like when you zoom out far enough to see the pattern. Van Ramsdonk wrote a paper in 2010 with the title Building Up Space-Time with Quantum Entanglement, and in it he described a thought experiment. Imagine a system of two entangled regions of space. Maximally entangled, they form a single connected space-time. One smooth region. Now gradually reduce the entanglement between them. As the entanglement decreases, the space-time starts to stretch. The regions start to pull apart. Reduce the entanglement to zero and space-time tears. The two regions are no longer connected. They have become separate universes. Entanglement is not just correlated with space-time connectivity. It is space-time connectivity. The wormhole is the entanglement. If you are sitting somewhere wondering why physics feels increasingly like philosophy, this is why. The frontier of physics is not in larger accelerators, though those help. It is in questions like, what is information? Can information be destroyed? Is reality fundamentally quantum informational? Does space-time have a substrate? These questions sound philosophical, but they have mathematical formulations and experimental implications. The distinction between physics and philosophy has never been more blurred. Now let us bring this back to the beginning, back to those two particles separated by the width of the universe. We said that one is measured and the other instantly knows. We can now tell a slightly richer story about what that might mean. They are not communicating. There is no signal travelling between them. They are connected by something that is prior to space, connected at the level of quantum information from which space itself is constructed. When one is measured, both collapse, not because one told the other, but because they were always at the foundational level, a single quantum object that the geometry of space-time had merely separated in appearance. The non-locality of entanglement is a window into the pre-spatial level of reality, the level where the rules that govern space have not yet kicked in, the level where the universe is not yet organized into here and there, close and far, now and then. It is not a glitch in reality. It is a glimpse of the reality underneath reality, the one that we do not have direct access to, the one that our senses and our intuitions are completely unprepared to perceive. And here is perhaps the strangest implication of all. If space-time is emergent, if it is built from entanglement rather than being a fixed backdrop, then the familiar picture of cause and effect, of events happening in sequence, of time flowing forward, may itself be emergent. The underlying quantum structure may have no preferred time direction. The arrows of time, the sense that the future is different from the past, the fact that we remember yesterday but not tomorrow, these might be features of the emergent classical approximation, not features of the fundamental reality. At the level of quantum information, past and future might be more symmetric than they appear. This connects directly to the delayed choice quantum eraser. The reason it does not feel paradoxical in the framework of emergent spacetime is that the entangled photons exist at the quantum information level as a single timeless object. The measurement events, which we perceive as happening at different times, are just different aspects of the same entangled state, expressed in the emergent space-time coordinates we use to organize our experience. The future measurement does not cause the past behavior. They are both manifestations of the same underlying quantum object, which has no inherent time ordering. This is not a comfortable thought. It is, in fact, deeply uncomfortable. It suggests that the rich, sequential, causally ordered world we experience, the world of before and after, of action and consequence, of memory and anticipation, is an extraordinarily successful approximation to something much stranger. We live in the shadow of a deeper reality that we can't directly perceive, can barely mathematically describe, and whose implications we are only beginning to grasp. The universe is not hiding from us. It is just built at a level that our minds were not designed to access. And yet we are accessing it. Through mathematics, through experiment, through the kind of stubborn refusal to accept comfortable answers that characterizes the best science. We designed machines that can isolate single electrons. We built detectors that can register individual photons after they have traveled hundreds of kilometers through optical fiber. We performed experiments across continents and across time, testing the fabric of reality at scales our ancestors could not have imagined. And what we found, every time, without exception, is that the universe is not local, that things separated by any distance can be connected, that measurement outcomes are random but correlated in ways no classical theory can explain. Einstein asked famously whether God plays dice. His answer was no. He believed the universe was fundamentally deterministic, that the apparent randomness of quantum mechanics reflected our ignorance rather than any genuine indeterminacy in nature. Bell showed that the only way to save determinism is to accept non-locality. Most physicists accepted quantum non-locality and abandoned determinism, or else, like the Bohmians, accepted non-locality explicitly as the price of saving determinism. Either way, the universe Einstein believed in, the universe of local, deterministic, objectively real properties, is not the universe we live in. What universe do we live in? One in which locality is emergent, one in which determinism at the quantum level is at best debatable and at worst genuinely absent, one in which two particles can be separated by all the space in existence and still in some fundamental sense be part of the same thing, one in which the act of observation is not passive but participatory, in which the question you ask determines what answer the universe gives, and asking a different question would have given a genuinely different answer, not just a different readout, but a different physical reality. That last point deserves to sit with you for a moment. When you measure the spin of an electron and find it pointing up, quantum mechanics does not say that the electron was always pointing up, and you just discovered it. It says the electron was not pointing in any direction before you measured it. The direction it points is a consequence of the measurement, not a pre-existing fact that the measurement revealed. You did not discover a property. You participated in creating it. In a very real, rigorously mathematical, experimentally confirmed sense, the universe needed you to look before it decided what to show you. This is what bothered Einstein more than anything else. Not just the non-locality, the incompleteness, the idea that reality is only determined when someone observes it. He found this philosophically unacceptable. "Does the moon exist when no one is looking at it?" he reportedly asked. "Of course it does," was his implicit answer. He was expressing not just a personal preference, but a deep conviction about what science should be. A map of what is really there, not just a tool for predicting what we see. Bohr's reply, approximately, was, "It is meaningless to ask about the position of the moon when no one is measuring it." Quantum mechanics does not describe what is. It describes what can be measured. Who won that argument? History has not given a clean verdict. Bell's theorem and its experimental tests prove that local realism is false. Einstein's intuition that things must have definite local properties was wrong. But whether reality depends on observation in some deep sense, whether the universe is in some way constructed by minds or requires observers to be real, is still contested. The many worlds interpretation avoids observer dependence entirely. Everything happens. No collapse, no special role for the observer. The Copenhagen interpretation depends on it, or at least sidesteps the question. The relational interpretation makes observation fundamental but distributes it. Every system can be an observer of any other system, not just conscious observers. The Bohmian pilot wave restores definite positions and avoids the problem differently. None of these interpretations can currently be distinguished by experiment. They all give the same predictions. We are in the strange position of knowing, with extraordinary precision, what the universe does, while being genuinely uncertain about what it is. The mathematical structure of quantum mechanics is as solid and well-tested as any scientific theory has ever been. The physical story behind the mathematics is one of the most actively debated questions in all of science, and that debate is not trivial. It is not physicists arguing about angels on the head of a pin. The interpretation of quantum mechanics has real consequences for how we understand consciousness, free will, the nature of time, the possibility of other universes, the relationship between mathematics and reality. These are not peripheral questions. They are the questions. If the universe has no properties until they are measured, what does that say about the existence of a world before observers evolved? If reality branches at every quantum event, do we have free will in any meaningful sense when every choice is made in every branch? If space-time is built from entanglement, what existed before the Big Bang, before space-time began? The particle physicists building the Large Hadron Collider, the cosmologists mapping the cosmic microwave background, the quantum information scientists building quantum computers, all of them are in different ways pushing at the same frontier, and quantum entanglement is at the heart of all of it, not as a curiosity, not as a footnote, but as one of the most fundamental features of how reality works. There is a common response when people first encounter quantum entanglement to reach for spiritual or mystical frameworks. The idea that two things separated by space can be connected, that consciousness might play a role in determining reality, that time might not be as fundamental as it seems. These resonate with intuitions that appear in religious and philosophical traditions across human history. The connectedness of all things. The role of the observer. The illusory nature of space and time. It is tempting to see quantum mechanics as a scientific confirmation of ancient wisdom, but this is a mistake, and it is important to be clear about why. Quantum entanglement is not about mystical connection between all things in a vague sense. It is about precisely defined correlations between specific particles that have interacted in specific ways. Correlations that dissolve rapidly through a process called decoherence, when quantum systems interact with the warm, noisy, complex environment of everyday matter. The quantum world is extremely fragile. Quantum computers require cooling to a fraction of a degree above absolute zero to maintain entanglement. Human brains operate at body temperature in conditions that would destroy quantum coherence in femtoseconds, quadrillionths of a second. The quantum effects that are so dramatic at the particle scale do not survive long enough to influence neural activity in any meaningful way. What quantum mechanics does offer, and this is genuinely profound without being mystical, is a revised picture of what reality is. Not a mystical picture. A rigorous, mathematical, experimentally verified picture that is simply much stranger than the classical picture. The strangeness is not in the eye of the beholder. It is in the equations. It is in the data. It is, in a very concrete sense, in the universe. The universe is non-local. The universe is, at some level, built from quantum information. The universe has no objectively definite state below the quantum level, or if it does, it achieves that definiteness through a mechanism that is itself explicitly non-local. These are not philosophical positions. These are conclusions forced on us by experiment, by reality, by the universe itself, which turns out to be far less willing to cooperate with our intuitions than we ever suspected. When Niels Bohr said that anyone who is not shocked by quantum mechanics has not understood it, he was being precise, not poetic. The shock is appropriate. The universe has handed us a description of itself that we cannot visualize, cannot intuit, can only compute. We have equations that predict the results of experiments to 11 decimal places, equations that have never been wrong, equations that govern everything from the structure of atoms to the light of distant stars to the chips inside the device you are using right now. And we do not understand what those equations mean. Not in the way we understand levers and pulleys and billiard balls. Not in the way we understand things. We understand quantum mechanics the way a calculator understands arithmetic. We can use it. We can apply it. We can build extraordinary technology with it. But asked what is actually happening, what is actually happening when two entangled particles are separated and measured, what the wave function actually is, what observation actually does, the most honest answer from the most honest physicists is, we do not know. And the reason that matters, the reason you should care about a phenomenon involving particles so small they make atoms look enormous, is this. Entanglement is not just a weird feature of subatomic physics. It is a clue about what the universe fundamentally is, about what space is, about what time is, about whether information is more fundamental than matter or energy, about whether reality is objective or participatory, about whether the universe we navigate every day is the real universe, or a kind of projection, an approximation that works beautifully at our scale but conceals an underlying strangeness that once seen cannot be unseen. The double-slit experiment revealed that particles can be waves. Bell's theorem revealed that nature is non-local. The delayed choice quantum eraser revealed that the boundary between past and future is less sharp than we thought. The ER equals EPR conjecture suggests that spacetime is made of entanglement. Each of these discoveries widen the gap between our intuitions and our equations. Each one moved the universe a little further from the familiar and a little closer to the incomprehensible. And yet, at each step, the universe remained comprehensible in the only sense that matters. It remained mathematical. However strange the physics, it continued to be describable in terms of precise, internally consistent equations. The strangeness did not dissolve into chaos. It crystallized into a deeper order that we can see in the math even when we cannot see it anywhere else. The universe may be non-local. It may be fundamentally quantum informational. It may be observer-dependent or many-branching, or piloted by waves, or constituted by transactions across time. But it is not random, it is not arbitrary, it is lawful in ways we are only beginning to understand. That lawfulness, that deep mathematical structure holding together even the most counterintuitive aspects of quantum reality, is perhaps the most remarkable fact of all. More remarkable even than entanglement itself. We found a universe that defies every intuition we have about space, time, and causality, and it still holds together. It still makes sense at the mathematical level. The equations still close. The predictions still match the experiments. Whatever the universe is doing at the level we cannot see, it is doing it consistently. There is something almost consoling in that. Not in a religious sense, not a guarantee that the universe has our interests at heart, but in a more basic sense, the sense that reality, however strange, is not arbitrary. The non-locality is consistent. The randomness is constrained by precise probability rules. The correlations between entangled particles are not random. They are exactly as strong as they need to be to violate Bell's inequality by the specific amount that quantum mechanics predicts. Everything is as strange as it needs to be, and not one bit stranger. The universe seems to have found the minimal configuration of strangeness required to be what it is. Two particles separated by all the space in existence. One is measured, the other instantly knows. That simple fact, those 20 words, contain within them the collapse of classical physics, the non-locality of Bell's theorem, the possibility of quantum communication and quantum computing, the conjecture that space-time is built from entanglement, the open question of what reality is in the absence of observation, the ongoing debate between the greatest physicists alive about the meaning of the most successful scientific theory ever devised. 20 words, and behind them the universe is far stranger than you were told. Everything you think you know about space, that it separates things, that distance matters, that far away means not connected, is an approximation. A very good approximation. An approximation good enough to build cities, launch rockets, cure diseases, and write equations that describe stars. But still an approximation. Underneath it is something that does not separate, does not require distance to be bridged, does not obey the rules that space seems to impose on everything. Underneath it, things that were once together remain together in a way that physics cannot fully explain, that no experiment has ever disproved, that forces us, if we are honest, to admit that we are living in a universe we do not understand. Not yet.